In this video, we will introduce nuclear chemistry. Chemistry is known as the science of change, and this change involves the study of chemical reactions. Now, so far, the chemical reactions that we have been studying have involved conservation of mass and conservation of matter. The identities of the elements don't change, and the reactions actually involve the electrons in the valence shells of each of these atoms. These reactions also involve only moderate amounts of energy, be it absorbed or released. And these experiments can be performed by even inexperienced chemists in an educational institute. By comparison, nuclear chemistry actually takes place in the nucleus of an atom. Now, these reactions involve tremendous amounts of energy. They do not necessarily conserve mass, and the identities of the elements change during these nuclear reactions. It also should be noted that experiments in nuclear chemistry must be performed by very experienced individuals and often involved very specialized equipment. Now, in order to understand what is going on in nuclear reactions, we have to revisit isotope notation. Here we have AZX notation. The atomic number, or Z number, tells us the number of protons in a nucleus. The mass number, or the A number, is the total number of nucleons. This is protons and neutrons. And then, as you may remember, the Z number, or the atomic number, actually gives us the identity of the element, and it will determine the element symbol. Now, again, in order to understand what is going on in nuclear chemistry, we have to understand the subatomic particles that are involved in these reactions. So we have our protons, neutrons, and electrons, as we already know, but then we introduce a couple of new ones. We have the positron, which is essentially the same as an electron, except it's positively charged. Think of it as an anti-electron. And we also have what's known as an alpha particle. Now, an alpha particle is simply a helium nucleus. The reason why we introduce this is that alpha decay is actually the expulsion of an alpha particle from the nucleus. It's a very common form of nuclear decay. Notice that gamma rays are not included in this particular list. This is because they are not technically particles, but high-energy electromagnetic radiation. Gamma rays are a product of the mass defect of nuclear reactions, and when some subatomic particles annihilate each other. Now, in order to understand what's going on in a nuclear reaction, we have to be able to balance these nuclear equations. Here we have the combination of two protons. We see on the reactant side of this nuclear reaction, we have two protons, each one with one proton and no neutrons. On the product side, we have a deuterium nucleus, or hydrogen 2, plus something else that's missing. We need to be able to find out what is missing. Now, in order to balance a nuclear equation, we have to balance the mass numbers, the total sum of the mass numbers on both sides of the reaction arrow, and the atomic numbers, the Z numbers, on both sides of the reaction arrow. In this case, the deuterium on the product side already accounts for the two nucleons in the products. But in this case, we're actually missing a Z number. Now, the only thing that can account for this is something with no mass number, or 0 for mass number, and a positive 1 for the Z number. Well, the only thing that fits that bill is a positron, which we write with a uppercase beta with 0 mass number and plus 1 Z number. In this reaction, we have uranium-235 being bombarded by a single neutron. Now notice the neutron has a mass number of 1 and a Z number of 0. And this is because there's no proton in it. One of the products of this nuclear reaction is xenon-92, and another product is 3 neutrons. This becomes important later on when we discuss chain reactions. Now we want to find out what is the missing daughter nucleotide of this reaction, xenon-92 being the other daughter nucleotide. Well, again, we need to account for the mass numbers and the Z numbers, or the atomic numbers, on both sides of the reaction arrow. So if we add up 1 uranium-235 and 1 neutron, and we subtract from that the xenon is 92 and 3 neutrons, we are missing a mass number of 141. We do the same for the Z number, or the atomic number. Now we don't have to worry about the neutron because it doesn't have a Z number, it doesn't have a proton in it. So we have the 92 from uranium. We're going to subtract from that what we know from the other side, the 36 from xenon, and well, that's it. There's actually no Z number in the 3 neutrons. And we get 56. Well, this means whatever our daughter nucleotide is, along with xenon 92, has a mass number of 141 and a Z number of 56. Well, the only element that has a Z number of 56 is barium. So the other daughter nucleotide is barium-141. In this reaction, we're trying to find out what spontaneously decays into polonium-218 and an alpha particle. Again, balance the mass numbers and the atomic numbers. First, let's find out what we're missing from our atomic number. So whatever reactant we had, it had to have a total mass of whatever we have on the product side, which is 222, and a Z number of 86. And again, the Z number is the most important here. That gives you the identity of the element. In this case, this is radon-222. So now that we've seen some nuclear reactions, let's talk about nuclear decay. One question is, why do atoms spontaneously decay? The very basic explanation is that the nuclei of radioactive elements is unstable. Why is it unstable? There's a lot of theories out there, but our basic explanation here is that you have to have the correct ratio of protons to neutrons in order to have a stable nuclei. In fact, the only element that is stable with no neutrons is hydrogen, or hydrogen-1. Now, in order to reach this band of stability we see here on the right, we need to either get rid of neutrons or get rid of protons. So in this case, beta decay, if we are above this belt of stability, will bring us back down. So for instance, tritium, or hydrogen-3, will decay into helium-3 plus a beta emission, or an electron emission. Carbon-14 will decay into nitrogen-14 along with an electron. And phosphorus-32 will go through beta decay, or beta emission, to form sulfur-32. Positron emission is what happens when we have too few neutrons. So in this case, we have, for example, potassium-38 will decay into argon-38 and a positron, and carbon-11 will decay into boron-11. Now, it should be noted that these positrons do not last very long. They will immediately be annihilated by a nearby electron and usually create very high energy electromagnetic radiation, such as gamma rays. Now, in electron capture, this is another way of getting back to the belt of stability, and what happens is that the nucleus will actually take in one of the lower energy electrons. Now, this does involve some energy, which we'll get to in another video. But for instance, we have argon-37 will go through electron capture and become chlorine-37. Aluminum-26 will capture an electron and become magnesium-26. And finally, we have alpha decay. Alpha decay is when an unstable nucleus will eject an alpha particle from its nucleus in order to become more stable. These elements are generally below the belt, but not always. And they almost always occur in extremely heavy isotopes, usually elements with atomic numbers greater than 83, although it has been seen in lighter isotopes. In these examples, we see polonium-212, uranium-235, radon-222, and bismuth-214 going through alpha decay in order to try to achieve a more stable nucleus.